Hello, guys. Welcome to another episode of CUDA Education. I have decided to basically start going down the road of ray tracing. So, ray tracing is all the hype. Definitely been the hype last couple of years, and it's the latest and greatest in computer graphics. And basically, the idea for ray tracing is that we we shoot a bunch of rays out programmatically, and then we traverse a scene and we get a realistic representation of what happens to light when these rays hit objects in our scene. So the biggest difference between a ray traced scene and a non ray traced scene is, generally speaking, how realistic it is. And of course, the video game industry has been on this heavily. Um, And the reason why a ray trace scene is better is because all of the interactions with the light. So whether you're talking about shadows or you're talking about mixing of colors, because the light hit one material, then it hits another material, and then um, the color of the light has been changed, and therefore you get an accurate reflection of what's what a realistic scene would look like. Previous to ray tracing, you would have a whole bunch of artists who would basically try to guesstimate or mimic where shadows would go, what shadows would do, etc., etc., how the colors will change, you know, all of those things, and you know, you wouldn't necessarily get a realistic representation, including even the objects in the scene. It wouldn't be, realistically represented. But with ray tracing, you could do that. What was the holdup? What was the big delay in making ray tracing possible? Basically, computation power. So now we have GPUs that are so well, what's the word? Just fast. Their processing power is unbelievable in 2024, that you could now have these things accessible to the public, to the to consumer level technology. This was usually something that was more in like studios, Pixar, and all of that. But now you could get that stuff, if you buy a computer with an RTX NVIDIA GPU, right? So that's all the hype with ray tracing. And my plan here is to basically go down the process of learning ray tracing and take you along with me. I haven't been doing computer graphics for 100 years. I don't know Elon Musk. I've never been on his yacht. Um, I don't know Bill Gates either. And I don't know the NVIDIA CEO or the AMD CEO for that matter. I'm just a regular guy learning computer graphics and taking you along for the ride. So listen, if you guys want to join in on the fun, if you want to be a part of this journey, um, tutorial number 1 and tutorial number 15 are the two tutorials that I have available online. I'll link them down below. And that will allow you to get all of these examples installed on your machine. Um, this code is courtesy of Sascha Willems, who is a computer graphics programmer that has made these examples freely available to anyone on the internet. And basically, you could use these algorithms to learn ray tracing. So and learn Vulkan for that matter. So this is a Vulkan shop here. We're trying to learn Vulkan. And what we're doing is basically, we work through these examples to get um, to learn Vulkan. Okay, so I'm now started on the journey of ray tracing. As you can see, I have a RTX 4050 laptop GPU. So we have previously discussed, the regular triangle algorithm, but the regular triangle algorithm doesn't have it doesn't have ray tracing, right? So this ray tracing basic is what we have. So if you guys want to join in on the fun, you definitely need you don't necessarily have to have an RTX, right? But for the ray tracing piece of it, which is this one, you do need an RTX GPU or an AMD GPU with ray tracing capabilities. I don't know which GPUs those are. You're gonna have to look that up on your own from AMD. But a ray tracing capable GPU, and yeah, basically a Windows machine. So a Windows machine, ray tracing capable GPU, RTX, NVIDIA RTX, any NVIDIA RTX generally speaking, has ray tracing capabilities. And then you will be able to run this script and learn Vulkan, carry along. So tutorial number 1 is installing the Vulkan SDK. Tutorial number 15 is installing these examples here. So you can see there are a lot of examples. I'm not going to go through them now. I'm sure in my other freely available YouTube videos you could see them. But tutorial number 1 and tutorial number 15, assuming you have a Windows-based machine and assuming you have for these examples here, for these ray examples, you need an a ray tracing capable GPU, and you can look it up online for the GPU you have on your machine, and and work your way through. So for this, what I wanted to do is basically for this video, what I wanted to do is just basically take a random walk down the script. So this is the most basic ray tracing example that's available, at least here and I think anywhere, but I don't know for sure. And again, this is courtesy of Sascha Willems. Please support, visit his website. Support. He is available online. He's also available on Reddit. Please support his website and his channel. And yeah, he has given us this script that basically goes through a ray tracing example. I'm learning it along with you, and that's basically what it is. So I guess I'll just walk through the code as best as I can, and then we'll talk about some stuff. So there's a lot of new vocabulary with ray tracing, a lot of new concepts, a lot of new things that are just been introduced to computer graphics, introduced to the API, what have you. So yeah, let's just go through the comments. So holds data for ray tracing scratch buffer as a temporary storage. So whenever you see buffer, I generally think of it as like a storage container. So it's just a storage container. It's like an allotted piece of memory, and it has special information in there, right? So we have this struct here that does that. We have a ray tracing acceleration structure, which I'm gonna have to discuss a little bit. So apparently acceleration structures now is, the way I like to think of it, it's like a blueprint of the screen. So it's like pre-processing, a blueprint of the scene. So it's like pre-processing sort of the actual scene that you're ray tracing. So think of ray tracing as like a scene, like like a movie scene or whatever, or a room or an objects in a room or something like that. But it's a scene, right, on your screen. And we have this. They have these things called acceleration structures, and it's basically a blueprint of what's in the scene, and kind of giving the system, the algorithm, Vulkan, an idea of, okay, what to expect where. Okay, that's generally what a acceleration structure is. That's in my definition. Believe me, you ask 10 different computer graphics programmers, you're going to get 10 different definitions on not just acceleration structures, but on anything, on shaders, on fragments, on what a buffer is, it this is one of the reasons why I am going about it this way, is that we run by examples. Okay, so if we have code and we see the code working, you could learn what it is and you could internally make a definition of what these words are and these objects are and these structures are. So we have an acceleration structure. We're not going to go too deep into it, but there you have it, right? And then you have some Vulkan example base. Now this is the Vulkan example base, I think, it's basically a basic set of code. So it's like a foundational set of code and functions and structures and things like that is used by all these other scripts. So I think it reads from here, base, and then all these other scripts, take different things from the base. Okay, so you have the base, and then all these other Vulkan example base. So this is taking from that base. I've sort of corresponded with Sascha at one point or another, and he has basically told me that, listen, people should use his base, his Vulkan example base, and especially when you're just learning, to maybe try and code on top of it. That's kind of the idea that I've gotten. He's like, I think the idea is that you don't necessarily have to or want to do everything from scratch. You want to take the sort of the basic foundation that he has and take advantage of it to focus on building what it is you want to build instead of doing everything from scratch. But you got to talk to him directly or whatever, communicate with him directly to verify exactly what it is. But here you're just using the base Vulkan example base to do a bunch of stuff. So all of these things here, as you can see, acceleration structure is all over the place. Ray tracing pipeline, buffer device address. Still haven't really figured out, there's a lot of device address hanging around, and I'm not, too well versed on why that is, but we'll leave it alone for now. So, and then we have our ray tracing pipeline. The ray tracing pipeline is different from the traditional computer graphics pipeline. This is all relatively new stuff. It's new to the API. So there's a ray tracing pipeline which is different from the regular just computer graphics pipeline. So we're gonna have to take heed of that too. In the acceleration structure, you do have top level acceleration structure and bottom level acceleration structure. There's code that kind of defines out what these things are. I personally haven't fully internalized what they are myself, but it comes up again in the code. So when it does, we'll discuss there. And then we have some like regular vertex buffer, index buffer stuff, transform buffer. There is also the concept of a binding table. There is a regen binding table, a miss shader binding table, regen shader binding table, miss shader binding table, hit shader binding table. Binding table is basically a record of what has occurred upon pushing the rays into the scene. That's how I define it. Might not be totally 100%, but basically you have rays that miss and you have rays that hit stuff, and the binding table basically records that stuff, right? The regen binding table itself, I'm not really sure exactly where that comes in, but you miss stuff when you push a bunch of light into a scene or push a bunch of rays into a scene. Rays are like light, right? And you shine. It's like you taking a flashlight and you're shining light onto a scene. Some of the rays are gonna go past the scene and they're gonna go into like the background or into outer space, into no man's land. And that's where you could do like a background thing, like whatever, where it just absorbs all those rays and like you see stars or something, or you see sky, or you see something. So you have rays that miss, but then you have rays that hit stuff. Now, when rays hit stuff, you gotta know that the rays hit stuff, right? So that's what this and this is about. Let's move on. Storage image, leave that alone for now. Uniform data, leave that alone. This is typical Vulkan stuff. We have pipeline layout, descriptor set layout. I've discussed this in previous videos. I'm not gonna get into it now, but remember, descriptor set usually means you're describing what objects are in memory. So you don't just give someone a blank USB stick. You actually label the USB stick, like this USB stick has images, or this USB stick has sound files, or this USB stick has Word docs. I don't know. But like that's usually what the descriptor set is about. It's about describing what is in memory and all of that stuff, right? All right, we're going back to base code now. You need a title for your script, ray tracing basic. We need a camera system, of course. We require at least Vulkan 1.1, ray tracing related extensions. This is Vulkan, guys. Like, it's almost as if Vulkan invented the English language, right? They love text so much, they love dialogue so much that it's just, anything new that Vulkan comes up with, they gotta sprinkle all kind of text over it, right? It can't be simple and straightforward. It has to have a lot of text. This code is about 900 lines of code. So there you have it. So we got to move because I haven't even reached 100 yet, but that's all right. That's all right. Vulkan guys, you're still my friends, right? All right, we're cool. All right, so there's a bunch of extensions that you need. Yeah, have a blast. Okay. Interesting point, we have this SPARE-V stuff. Remember, SPARE-V is sort of like a proprietary language that is used to help with driver compliance among different devices and all that stuff. But previous videos talk about that, I think. But yeah, so we have a bunch of extensions for acceleration structure, and we have SPARE-V. And then we have to destroy stuff. So for all you hardcore programming guys, you know what destructors are. These are, you create stuff and you have to destroy stuff. So destroy the pipeline, destroy the scriptor set, destroy the images, destroy the memory. Are we destroying anything? Okay, we're destroying acceleration structures. We're destroying, what else are we destroying? Okay, we're destroying the regen shader binding table, the miss shader binding table, and the hit shader binding table, right? Uniform buffer object. So, we create stuff, we have to destroy stuff. And remember, that's good programming practice. You have to have good housekeeping with this stuff, right? You don't want to be using stuff, creating stuff, and then just have it hanging in memory and using up memory even when you're done using it, right? Because it will eventually eat into your RAM, and it will eventually eat into the memory that you have in your system, and then your system becomes unstable if the program is running for a really long time and all of that stuff. All right, so that's good. All right, so scratch buffer. So we're creating a container to hold temporary data for the ray tracing acceleration structure. Yeah, here you go. Okay. All right, and right, we have create scratch buffer, and then we have delete scratch buffer. So I guess this is a housekeeping thing. You have to delete it also when you're done with it. Create acceleration structure buffer. So anytime I see the word buffer, in my mind, I just think it's a memory container. So it's a bucket where you know, so only specific things can be held in that bucket. Only specific things can be held in that container. So there you go. This is the acceleration structure buffer, right? And there you have it. And then, yeah, now we get into the gets device address from a buffer that's required for some of the buffers used for ray tracing. Let's go. Let's go, guys. We're at line 200. Let's keep focused. So get buffer device address, and yeah, it's something that needs to be done. So get buffer device address, and we do that. Set up a storage image that the ray generation shader will be writing to. So I believe this would be, I guess you have to record what happens. I don't know. Create storage image. I guess I'll learn once I get into, once we get into it more. But this is it here. Create storage image. Okay. One of the things I intend to do too is try and tinker with the code, right? So you know how I roll, right? I try and modify things in the code to see what happens, and then from seeing how the output changes, you learn why these things exist and why they're important. So like even with the regen stuff, I plan on saying, okay, let the regen shader binding table be empty, right? So my guess is if it's empty, then no rays will be, I don't know, no rays will be shot, and then we'll have a blank screen. Let's say I make the hit shader binding table empty, right? I force it to be empty. I don't put anything in there. Then I also expect to see to basically see a blank screen, right? I don't know. And then I'll tinker with the miss shader binding table and see what happens. But yeah. So that is create acceleration structure buffer. Right. Okay. Right. So now we're getting into bottom level acceleration structure contains the scene's actual geometry, vertices, triangles. Okay. So remember I said acceleration structure is like a blueprint of the scene, right? So it's like a pre-processed blueprint of a scene. So I guess the bottom level acceleration structure now will have vertices of the triangle. And and these are the vertices. Now I will admit this is sort of the updated, this is the ray tracing version, but these coordinates, man, like at least not in this ray tracing one, but in the regular triangle one, the coordinates just don't make. I think it was more elaborate than this. I don't want to go to it because I don't want to confuse you guys, but it was more elaborate. It wasn't as simple as this. It was like you had three more coordinates for each line or something, right? So yeah, it just never I learned X, Y, and Z in school, but apparently there's like three other indices or whatever. Anyway, the bottom level acceleration structure is supposed to contain right, contain scene's actual geometry. So it will contain the vertices for the triangle, all right? And here you have it. And then you set up indices 0, 1, 2. So remember programming, we start counting from 0. So, naturally a triangle, you would have 3 indices, right? Set up identity transform matrix. Now, this is also something that, I'm not quite sure. I don't know if this is for like when you're moving the triangle, like you move it with the mouse and you adjust it, that this does something with it. Not really sure. All right, create buffers. For the sake of simplicity, we won't stage the vertex data to the GPU memory. So right? There's a whole staging buffer conversation. I have videos on that. But thank God, because we're already at like 1,000 lines of code. He's just doing this for simplicity's sake. So basically, what it is I know this VK memory property host coherent bit and then host visible. I know these guys are for like basically using a set of memory that is visible by the GPU and the CPU. So remember, guys, in computer graphics, we're dealing with the GPU, but your computer system, you need to make a distinction between what's going on with your GPU and what's going on with your CPU. Your CPU is usually maybe like an Intel CPU or an AMD CPU, and then your GPU might be NVIDIA, right? So obviously your NVIDIA GPU has memory, and your regular CPU computer has memory too. And what this is saying right here is that whatever memory we use, it can be seen by both the CPU and the GPU, right? So that's my contribution to this discussion right here. All right, so index buffer. So vertex buffer, index buffer, transform buffer. So yeah, I'm gonna have to dive into what the transform buffer is all about. Don't know at this point, but here you have it, right? So we're just making all of these things visible by the host and the by the host, which is the CPU, and the device, which is the GPU, right? Now, if you're optimizing this generation of a triangle, you would do more things to like maybe just put everything in the GPU so that it could be retrieved faster and all that stuff. But we don't care about that. We just care about seeing generating the triangle, right? We're not trying to make the next Grand Theft Auto or Cyberpunk or something, right? We're just creating a triangle. So thank God for simplicity, right, guys? All right. So all of this stuff have to research. Take a look at the spec. Oh, also, guys, if you want, any of these special things right here, like you could generally Google them and look in the spec, in the Vulkan spec, and they will tell you exactly what they are and what their purpose is. Yeah. All right. We have some device address conversation again, which I'm not going to get into. And then we're building acceleration structure geometry. So yeah, we're at line 300. How long is this? Okay, we're already at 30 minutes. You still there? Anyway, so we have this stuff here. Right, so create a small scratch buffer used during build of the bottom level acceleration structure. So again, this is it's almost like a draft paper, if you will. So you're trying to yeah. So that's for the bottom level acceleration structure. On the device. Device usually means GPU, right? Via one-time command. Some implementations may support acceleration structure building on the host. But we prefer device builds. Okay, so apparently we're team device builds, right? I don't know. We prefer the device builds. Okay, so we know the bottom level was the vertices for the triangle. The top level acceleration structure contains the scene's object instances. Yeah. I'm team bottom level structures. I don't know what top level acceleration structures. At this point, I don't fully understand it, but it's fine. Create top level acceleration structure. So this instances, right? Object instances. I guess it, different objects in the scene, right? Um, Storage container for instance data. So I'm gonna guess maybe top level acceleration structure, like you could have multiple triangles, right? So multiple instances, multiple triangles. I know there's an example where it's like a planet. It's this guy, a planet, with multiple rocks going around the planet, kind of like Saturn, but instead of with the rings, it's like rocks, and all of those rocks are instances. So maybe that's what that is. Buffer for instance data, right? And then we're back to device or host address. All right, we're halfway through, guys. We're almost done. Well, not really, but halfway through. Yeah, I'll leave that alone. Um, we're creating draft paper again. All right, so let's get to shader binding tables that binds the programs and top level acceleration structure. Shader binding layout used in this example, regen miss hit. Shader binding table layout. Okay, so this function creates the shader binding table. Um, we'll have to get into that. All right, create this descriptor set. So remember again, guys, um, descriptor sets usually means that you're trying to um, describe things in memory. It's not just a blank USB you're handing over to Vulkan. You're actually trying to describe what's in on the USB, like what's in memory. So that's what I think of when I think of descriptor sets. All right, create our ray tracing pipeline. And then that's all of this. Set up ray tracing shader groups, ray generation group. All right, so here you go. Miss group and closest hit group. Create the ray tracing pipeline. Create the uniform buffer used to pass matrices to the ray tracing ray generation shader. All right, we're at line 700. I think uniform buffer usually is data that's changed frequently. Um, Again, it's coherent between the CPU and GPU. Okay, if the window has been resized, we need to recreate the storage image and its descriptor. I'm going to go out on a limb and say this reminds me of when you're resizing for just regular scripts that are not ray tracing. You have to recreate the swap chain because, of course, the images that you're displaying in the window has now changed because you've changed the size of the window. So I don't know if this has this concept of the storage image. I don't know if that has something to do with the swap chain. And then of course the descriptor is like describing what's in memory and all of that, right? So you're destroying the lead allocator. So you're destroying the image and the image view, and we're freeing the memory, and then you're recreating it. So we have a lot of things to discuss with that. All right, build command buffers. You guys are familiar with command buffers, right? What it is that we're trying to do. um, Set up the buffer regions pointing to the shaders in a shader binding table. Dispatch the ray tracing commands. I know this VKCM bind pipeline is super important, and this VKCM bind descriptor sets. Copy ray tracing output to swap chain image. Prepare current swap chain image as transfer destination. Aha, so we do have a swap chain after all. Prepare current swap chain image as transfer destination. Prepare ray tracing output image as transfer source. Transfer source. Okay, I know a little bit about this. Right, there's a source and destination thing. And we're moving things from one to the other. And then, okay, so I guess this, so I was kind of right after all. So this storage image is being basically moved on to the swap chain, right? So makes sense. Maybe this is what connects old from new or new to old. Prepare ray tracing output image as transfer source. So the ray tracing pipeline is completely different from the regular computer graphics pipeline. I think I mentioned that earlier in the video. All right. So there's an output from the ray tracing pipeline, and I assume now we're moving it over into the swap chain, which I know is like old computer graphics concept, right? Where but I guess a swap chain is a swap chain, right? And you need a swap chain to like display stuff on a screen. So maybe it's neither new or old. It's just part of the foundation of computer graphics, right? But you're doing stuff with ray tracing here, and then you're moving it over into the swap chain, which makes sense. Transition swap chain image back for presentation. All right, so I guess right. I guess you're putting what I think this means, transition swap chain image back for presentation. So in my other videos I talk about taking like sort of what you would say the canvas, or taking the piece of paper out of the swap chain, drawing on it, and then putting the piece of paper back into the swap chain for it to be presented, right? So when I see this transition swap chain image back for presentation, so when I see this in my mind, I'm thinking, okay, we've already copied over the ray tracing output image back onto the canvas of the blank swap chain image, right? That we pulled. So we pull the blank swap chain canvas, we drew on it, and then we're putting it back into the swap chain so we could present to the screen. That's what I think. That's what I think when I see this transition swap chain image back for presentation. Okay. Now, transition ray tracing output image back to general layout. So this now is after, in my interpretation, after um, the ray traced image has been either moved over to the swap chain or transferred to the swap chain or used by the swap chain and presented, that you need to do a reset, right? You need to clear the canvas so you can start the process over again. So I think that's what this is, but don't quote me because I might be wrong. Right. Enable features required for ray tracing using feature chaining via pnext. Okay, so yeah, this is where, so if you try and run this script without a ray tracing capable GPU, you will get you'll basically get, it's a specific extension, but it basically says that the ray tracing extension is not found, right? So yeah, so this is, I think maybe this is get enabled feature. So this is where it might all fall apart, because if you don't have a ray tracing capable GPU, then you won't be able to you won't be able to run the script. And then, right, so we're back to example base. Get ray tracing pipeline properties, which will be used later on in the script. So that's this guy here. Get acceleration structure, which will be used later on in the sample. In the sample. Get ray tracing acceleration structure related function pointers required by this sample. So create the acceleration structures used to render the ray trace scenes. So draw function, render function, and that's it, guys. So 900 lines, 910 lines of code. All right. So a special shout out to all the haters, all the people that are gonna say, oh, X, Y, and Z. Just understand, this is new technology. Very few people in the world know this stuff and know it as well to actually generate 900 lines of code to create a ray trace triangle. All right. So first of all, be thankful. And for all you haters, like, whatever. So this is gonna be my project. I think ray tracing is new and exciting. I mean, I personally want that is always in sort of computer graphics and in movies and entertainment and even in just every facet of life. It was always, when are we gonna get to having graphics be realistic, like absolutely 100% realistic? And I think this ray tracing stuff is really, really cool. And believe me, NVIDIA is profiting massively from this stuff. Okay, it's not just AI, but it's also, the ability to make realistic scenes, whether you're talking about, real estate simulations, construction simulations, all of that stuff. And NVIDIA is making billions and billions and billions of dollars selling the hardware so we could do this stuff. Problem is, not many people know how to do computer graphics in general and specifically ray tracing. So it's definitely worth your time. If you want to join in on the fun, if you have a Windows-based machine with a Vulkan-capable and a ray tracing-capable GPU, you will be able to install these examples and run the ray tracing examples. Now, if you don't have a ray tracing capable GPU, but your GPU is Vulkan capable, you could still join in the fun, because all these other examples here are really good examples, and you will be able to learn computer graphics. So don't despair if you don't have a ray tracing capable GPU. You could still learn a lot from my the tutorials I have online, and also these Vulkan API discussion videos. So that's it, guys. Support the cause. Tell your friends. Get your friends together. Like, the thing about it too is that you don't just want to be learning this stuff by yourself. Get a bunch of your friends together, like on the weekends, or in the evenings after work or school or whatever, and get a bunch of your friends together, and try and decipher this stuff. Run the different examples. And learn. Sure, you want to play video games and stuff, but you also want to learn something, right? And I think the world is going more and more digital. That's obvious. So your ability to learn, or your ability to generate computer graphics and to visually represent data and visually represent whatever idea you have in your head is an endeavor worth working on. It's going to take time. I mean, even me, I've been at this stuff for years now, and I still obviously don't know everything, and they still keep introducing new stuff. So yeah, guys, thank you for watching. Have a great day. I will try and make another video soon talking about more specific stuff, but we have at least gone through the basic the basic script for creating a ray traced triangle. All right. Have a good day.